Light is the connection between us and the universe. Through light, we can see distant stars and look back at the beginning of existence itself. But what is light? In a nutshell, light is the smallest quantity of energy that can be transported, a photon, an elementary particle that cannot be split, only created or absorbed. Light also has a wave-particle duality, being kind of a particle and a wave at the same time. Although there are more complicated explanations, but we will leave it at this. When light interacts with matter, it is either refracted, in other words transmitted, it can be reflected at the boundary or absorbed entirely. Where does light come from? Vast amount of electromagnetic radiations is emitted when atoms or molecules drop from a higher state of energy to a lower one. They lose energy and emit it in the form of radiations. At a microscopic level, visible light is created when an electron in an atom that is in an excited state drops to a lower energy state and loses this excess energy. In the same way, an incoming light can elevate electron to a higher state of energy by being absorbed by it. The moving charge of an electron creates an oscillating magnetic field, which creates an oscillating electric field perpendicular to it. These two fields move themselves through space, transferring energy from one place to another. Although when we say light, we actually mean visible light, but this is a tiny part of electromagnetic spectrum. In reality, light refers to the total electromagnetic spectrum as it is propagated by both electric and magnetic fields, oscillating perpendicularly. Electromagnetic spectrum consists of an enormous range of wavelengths and frequencies. But what makes visible light special? Well, absolutely nothing. We just happen to evolve eyes that is good at recognizing just this part of electromagnetic spectrum. We can represent light as a wave. Just like any other wave, light has a wavelength, frequency, and a speed. Different colors of visible light have different wavelengths and frequencies, and so does the rest of the electromagnetic spectrum. In case of visible light, red has the greatest wavelength, while violet has the least wavelength. We can see this because as we move down from red to violet, the waves start to come closer. It is important to remember the order of visible spectrum, with red at the top and violet at the bottom. A useful trick to remember is through mnemonic device Roy G. Biv. In this, R stands for red, O for orange, Y for yellow, G for green, B for blue, I for indigo, and V for violet. Let's recall our wave equation from chapter 13. V equals to F multiplied by lambda. In this case, V stands for speed of a wave, F for frequency, and lambda for wavelength. We can rearrange the equation as follows. Lambda equals to speed divided by frequency of the wave. As speed of light is a constant value, our equation tells us that wavelength and frequencies are inversely linked. This means a wave of higher wavelength, such as red, will have a lower frequency. Similarly, a wave of lower wavelength, violet in case of visible light, will have a higher frequency. We can also see this in the image to the right. As we move downwards from red to violet, the number of waves in each second decreases. In other words, frequency of wave increases. So there is an inverse link between wavelength and frequency. When a beam of light hits a piece of glass straight on, it passes right through it, but the waves that make up the light actually slows down in the glass and only return to their normal speed when they come out of the glass from the other side. That slowing down is what causes white light to split into a rainbow of colors when it hits the glass at an angle. It happens because glass slows some colors more than others, and because slowing down at an angle makes light bend. It is easy to understand the bending if we picture how the white light looks from above. White light is a mixture of different colors. We discussed them using our mnemonic device, Roy G. Biv, in the last session. While white light contains all colors, it helps to look at one color at a time. When a wavefront of red light hits a glass at an angle, part of a wave that enters the glass first gets slowed down more than the rest, and that changes the direction of the whole wave. Violet light gets slowed down even more by the glass, so it bends more. All the other colors get bent somewhere in between. So the colors get separated when they first enter the glass on an angle, and they spread out even more when they speed up on leaving the glass prism. The reason different colors slow down by different amounts is because they have different wavelengths. Red light has the longest wavelength, followed by orange, yellow, green, blue, indigo, and finally violet, which has the shortest wavelength. Shorter the wavelength, the longer it takes to travel through glass. This is because the spectrum interacts with electrons in the molecules that make up the glass. Longer wavelengths, like red, only interacts little with electrons because of its low frequency, so it's not slowed much. Shorter wavelengths, such as violet light, has higher frequency, so it interacts with electrons more. It gets slowed down more and suffers greater deviation in its path. So its combination of light hitting glass at an angle and different wavelengths interacting with the electrons in glass in different amounts due to varying frequency, we see white light splitting up into a spectrum of colors. This is known as dispersion of light. We know that white light splits into a spectrum of colors when it enters a glass prism at an angle. Red color is at the top of the spectrum, while violet at the lower end. This all occurs because white light is a mixture of different colors that get separated in the denser medium. But what happens if a single ray of light strikes the glass prism? Will the spectrum still be produced? In this case, a red laser light is incident at an angle to the glass prism. As it is a ray of one color, it cannot split further into any other color. So the red light will be transmitted into the glass prism, where it will slow down and then later emerge from the other side at the same speed as the incident ray. So a single ray is only refracted by the medium. No dispersion is possible as the single ray does not contain a mixture of colors. Dispersion of light refers to splitting up of white light when it enters a denser medium at an angle. This happens because white light is a mix of different colors, and each color is slowed by different amount upon hitting the glass surface. The order of the split is important as it segregates each color according to the wavelength and frequency. The mnemonic for remembering this order is Roy G. Biv, with red having the longest wavelength and shortest frequency, while violet having the shortest wavelength and highest frequency in the visible spectrum.